right? Right. So let us start with relative velocity. So, like I said, the two modules you can expect for your first assessment is kinematics as well as statics. Now, under kinematics, we have 3 units, right? Those 3 units are relative velocity, resulting velocity, as well as projectile motion, right? So we are going to start with relative velocity, right? We are going to look at how the concept of relative velocity, how we attempt problems based on relative velocity, right? So number one, what is relative velocity, right? Now, relative velocity is essentially the velocity of one object compared to another. Simple, straightforward, right? Um, any and all velocities are essentially relative, right? If you say, for instance, there's a car moving on the road, right? And you look at your speedometer and the car is moving at 100 kilometers per hour, right? That car is actually moving at 100 kilometers per hour relative to the ground, right? So n and all velocities are relative, right? The the velocity of an object is always relative to, or let me say, the relativity of the object's velocity depends on the platform that it is on, right? Now, if, for instance, you have a car moving on the road, right, and you say the car is moving at 100 kilometers per hour, like I said, right, that car would essentially be moving at that speed relative to the ground. So, n and all, essentially, velocities are relative, right? Now, the way we express relative velocity mathematically, right, is if, for instance, you are told to calculate the velocity of A relative to B, right? Say you are told to calculate, so calculate the velocity of object A relative to B, right? Now, mathematically, this is what this means, right? When you are asked to calculate, so you have two objects, A and B, right? And you are told to calculate the velocity of A, right, relative to B, right? The way we look at this mathematically is the velocity that you're looking for, which is the velocity of A, means that A we are going to take as the object, right? So because we want the velocity of A, it means A we are going to take as the object, right? And the velocity it is being compared to, so relative to B. So it means that since we want the velocity of A is the object, right? Relative to B, that makes B our frame of reference, right? So in order to be able to do relative velocity, you need to have an object which we regard as the object, right? And an object which we'll regard as our frame of reference, right? So essentially, mathematically, right, how we would denote what they are looking for here is by saying they are looking for the velocity of A. So the first letter represents the velocity of the object, right? And the second letter represents the velocity of what represents our frame of reference, right? So for relative velocity, you have an object as well as its frame of reference. I will clear you,
Yes,
Yes,
sir.
sir.
right? Now, on a, let me say, if the objects are parallel to each other, right? If the objects are parallel to each other, mathematically, this is how we express the velocity of an object relative to its frame of reference, right? So in such a case, we would then say this is assuming that both A and B are parallel. So meaning, say you have A, right, and you have B. Say that's A, say that's B, right? So that's what I mean by both objects are parallel, right? So if both objects are parallel, the way we would express the the velocity of A relative to B would be to say V VA minus VB, right? This is how we would express that. So this here, right, how we would express the velocity of A relative to B is by saying we are actually looking for the velocity of A minus the velocity of B, right? That is for parallel objects, right? Parallel objects you can look at on your own. Parallel objects are pretty straightforward, right? If you have any questions regarding the relative velocity for parallel objects, right, you can ask me privately, right? We are going to cover relative velocity for non-parallel objects. So parallel that are essentially maybe one is either parallel to, or let me say objects that are not parallel with each other, right? So essentially we look at the objects relative to the Cartesian plane, right? That is what we are going to look at, right? Objects that aren't necessarily parallel to each other, right? We look at them relative to the Cartesian plane, right? So that is what we are going to look at. Are we clear? So by that, I mean, what we are going to look at is, say now, you're being told to calculate the velocity of A relative to B, and say A is in that direction, right? Take this as the velocity of A, right? And then maybe B is, say, in that direction. Let's make this one blue, right? As you can see, this object, and say this one is making an angle of 40 degrees with the x-axis, right? As you can see, I forgot to write here, call this VB, right? As you can see, both these vectors or both these objects are not parallel to each other, right? So we look at them relative to the Cartesian plane, right? So that is what we are looking at. That is what we refer to as relative velocity on non-parallel planes or on non-parallel objects. Are we clear?
Yes, sir.
Right. Now, even on such a case, right, because we're still looking at relative velocity, right, we're still going to look at which objects are we taking as the object and which are we taking as our frame of reference, right? Now, in determining the velocity of an object relative to its frame of reference, we, how can I put this? We make use of two methods, right? One method is the method of components, right? So you would, if, for instance, you have an object that is at an angle with the Cartesian plane, right? You would resolve that object or that vector into its components, right? Thus applying the method of components, right? Of which the resultant, right, of those vectors using the method of components would become, or you would regard as the what? As the velocity of the object you're looking for relative to the frame of reference. Right? The same could be said for resulting velocity. Right? So for when using the method of components, right, any and all vectors that need to be resolved, you resolve them, you get their components. Their components will align with the Cartesian plane, and then you are able to apply conditions of equilibrium. Right? You guys still remember conditions of equilibrium? Right? Remember, with conditions of equilibrium, you are only able to apply conditions of equilibrium if your vectors are such that they align with your axis. So by that I mean your vectors should either be parallel to the y-axis or be parallel to the x-axis. right? If your vectors are such that they are oblique, you have to resolve them. Once you've resolved them, right, the components thereof will then align with the Cartesian plane, and then you'll be able to what is this? You'll be able to apply conditions of equilibrium. Right, that is the method of components. Right, so that's method number one. Method number two is essentially the parallelogram method, right? Or you can call it the vector diagram, right? Because the vector diagram, there's two ways you can do it. You can either draw the parallelogram, or you can use Bose notation, right? I first will be teaching you the parallelogram method, right? Once you're comfortable with that, I'll then teach you how to use instead the use Bose notation, right? Draw a vector diagram using Bose notation, right? But only once you are comfortable with the parallelogram. I will clear you.
Yes, sir.
Right. Now let us look at an example. Right. So first we are going to look at using the method of components. Right. See how you'd go about using the method of components. Can you guys see this problem?
Yes, sir.
Yes, sir.
Why am I talking to one or two people?
Yes, we can say
Yes,
it.
sir.
Yes, yes. Say something. Say something.
Remember, you said you must cut off the mics. We don't want to disturb.
So by cut off the mics, I meant so that maybe if your kids are playing around, they do not disturb us. But if there's something to be said, turn the thing on.
Well noted.
So, all right, let us look at this problem, right, and see how we would use the method of components, right? And then afterwards, we will do the problem again, but now using the parallelogram method, right? It is important that you are comfortable with both methods because in the exam, it could be specified, right, for you to use the vector diagram, right? Now, probably for most of you, you are going to, the method of components, right, is the method that you are going to resonate with because you are used to, what is this, resolving oblique vectors into its components, right? You are used to, or you are more familiar with applying conditions of equilibrium, right? But you also need to be comfortable with the parallelogram method or the vector diagram method, right? Because, like I said, the examiner can specify that using the vector diagram calculates such and such. Right? So, if you're only comfortable with the method of components, in such a case, it will pretty much be curtains for you. Are we clear?
Yes, sir. Yes, sir.
All good.
Yes, sir.
All
Yeah.
good.
All right. Now
Yeah,
let us
Mister.
look
Yes,
at this
sir.
problem. All right, sure. Let us look at this problem. You have three cars, A, B, and C. Leave the fork for the road as shown by the diagram in figure 1 below, right? So we are considering these three objects. You have car A, car B, car C, right? Now they are saying calculate the velocity of car B with respect to A, right? So my question to you first is, when they say calculate the velocity of car B with respect to A, between A and B for 1.1.1, which is the object and which is our frame of reference? So one person can answer at least.
The car B's object.
I'm raising my hand.
All right. So I cannot quite see if someone is raising their hand, right? Because I'm busy using this platform, right? That is why I need for at least one person to say something, right? So yes, car B is our object, meaning car A is the frame of reference. Now, regarding what is this? Regarding relative velocity, right? The way we are going to express relative velocity on the Cartesian plane is by doing this, right? The object, right? The object that we take, or the velocity of the object that we take as our object, right? On the Cartesian plane, you are going to draw it the same way or in a direction that is the same as the one you've been given, right? So meaning, seeing that we've established that for this problem in particular, 1.1.1, B is our object. So we are going to draw the vector for car B in a direction that's been given on the diagram, right? And then the vector for our frame of reference, that one will draw on the Cartesian plane in a direction that is opposite the one we've been given. This is what I mean by that. B, we've established, is our object. B on the diagram is headed south, so we are going to draw B on the Cartesian plane headed south. Same direction as the one that's been given. Why? Because B is the object. So the object, you draw in a direction, right? You draw in a direction as the one you've been given in the problem. So B is the object. So we look at where B is headed. B is headed south on the diagram. So we're going to draw B headed south. Whereas with A, since A is our frame of reference, we are going to look to draw A in a direction that is opposite the one that you've been given. Are we clear?
Yes,
Yes,
sir.
sir.
Right.
Yes, sir.
Right now, so this is 1.1.1. Right. Here's our Cartesian plane. Right, here's our Cartesian plane. So now we are going to draw vector B, right, going downward, right? Because B is our object, we are going to draw B exactly how it's been drawn, right? Or in the direction that's been given in the diagram or in the problem. So B is going south, so we draw B as going south. Right, so that is B here. So that is B. So this we take as VB, right? Now, because we are using the method of components, right? Let me write here. Because we are using the method of components, right? Because we are using the method of components, we are going to express our vectors, right, based on the direction they are taking, right? Or based on which between the x and y axis is it aligning with, right? So by that I mean, if we look at the vector for object B, it is parallel with what? With the y-axis. So instead of just calling this VB, we are going to call this VBY, because since we're using the method of components, it essentially represents, right, the velocity of B in the what? In the y direction. Are we clear?
Yes.
Yes,
Got
sir.
it.
Yes, sir.
Right. So
Yes, sir. Clear.
because B is parallel to the y-axis, right? Instead of just calling this B, because we're using the method of components, right? We're gonna name it relative to what? Relative to the axis that it is parallel with. It is parallel with the y-axis. So instead of just calling it VP, we're going to call it VPY. Basically saying that this is relative to what? To the y-axis, or this aligns or is parallel to the y-axis, right? And then with respect to A, so A being a frame of reference, we are going to draw on the Cartesian plane in a direction that is opposite the one we've been given, right? Now, they said the the angle between B and C is 120, right? So essentially the angle from the x-axis, because remember here, you have a Cartesian plane, right? You have a Cartesian plane here, right? So meaning, since we know that's 90, it means this angle is equal to what? 30 degrees, right? Hence, this being 120. Are we in agreement here?
Yes,
Yes,
sir.
we are.
Right, and then here we have the y-axis, right? Now we know that this here is 90, right? But now we have a vector here, right? We have a vector here, right? So if this is 30 degrees, it means that's 60 degrees, right? So if this is 60, right, then what is this angle going to be? 60. Right. So this angle, right? So this angle is 60 degrees. It means this angle from the x-axis is equal to what? 30 degrees, right? Now the oblique vectors, you must make sure that the angle that they're at, right? You must make sure that you always reference their angles from the x-axis, right? So meaning we aren't going to use the 60 degrees. The 60 degrees is measured from, right, from the y-axis. So we are going to make use of 30 degrees because that's the one that is measured from the x-axis. The reason for that is so that when you resolve this vector into its components, the horizontal component, seeing that the angle is referenced from the x-axis, the horizontal component will be in terms of cos, and the vertical component will be in terms of sine, right? For resolving a vector into its components, right? If you want your horizontal components to be in terms of cos and your vertical components to be in terms of sine, then the angle you use must always be referenced from the x-axis. Are we clear here?
Yes,
Loud
sir.
and clear.
Right. Now,
Yes, sir.
vector A, right, is at an angle of 30 degrees from the x-axis, right? This is the direction you are given, but since car A for problem 1.1.1 is a frame of reference, we have to draw it in a direction that is opposite the one that we've been given, right? So opposite this direction means, remember here we have 4 quadrants, right? Opposite of this, it means this vector will fall on this quadrant. Are we in agreement here? Right? Opposite of this direction
Yes.
would be this direction. So this essentially we are going to draw going in this direction. Are we in agreement here?
Yes, sir.
Right?
Yes,
bearing
sir.
in mind that car A is a frame of reference. So in drawing car A or the vector for A, right, we must draw it in a direction that is opposite the one that you've been given, right? Now we know that this vector is making an angle of 30 degrees with the x-axis. So when drawing it, right, when drawing it here, right, when drawing it, we know this angle is going to be equal to what? 30 degrees, right? That we've already established that the vector A is at an angle of 30 degrees with the x-axis, right? Hello?
Yeah.
Yes, sir.
Right, so this is VA, right? So VA, we are going to leave as VA. Why? Because it is an oblique vector, right? It's only its components that are going to be in terms of the axis that they are parallel to or parallel with, right? Now, if you look at the vector for car B, Car B, they said, is going at 100 kilometers per hour, right? This is going at 100 kilometers per hour. That means essentially VBY,
110 kilometers per
yes,
hour.
this is 110 kilometers per hour, right? And then VA, we are told it is going at 160. Do we see this here?
Yes. Yes, sir.
Yes, so
VA going at, what is this? 160, right?
Yeah.
So this here is 160. This is 160 kilometers per hour, right? Now, as you can see, VP is parallel to the y-axis, so it doesn't need to be resolved, right? VA, however, is an oblique vector, right? So in order for us to be able to apply conditions of equilibrium, it means we have to resolve this into its components. So resolving this into its components, we already know we are going to have a horizontal component, right, going in this direction, as well as a vertical component going in this direction.
Yes, sir.
Right? And then here we have VAX, right? So this one we call VAX because this component is parallel to what? To the x-axis. So we have VAX is equal to, right? The hypotenuse here is VA. VA is 160, right? Because it's a horizontal component and our angle is a reference from the x-axis, this will be expressed in terms of cos. So cos 30, right? And then this one, this component is VAY, right? It's VAY because this component is parallel to what? To the y-axis. So this will then be equal to, now, the direction, right, of this component is south. And south we take as negative. So this is negative 160, right? It's a vertical component and our angle is a reference from the x-axis. So we use sine. Right? That is why it is important to always reference your angles from the x-axis. That way, you know your horizontal component will be in terms of cos, the y component will be in terms of sine. Are we clear here?
Yes, sir.
So,
yes, sir.
Are there any questions so far?
yes, sir. I just want to know, why is the green going down to the right? Shouldn't it go up to the left?
Okay. So shouldn't it go in this direction, right?
Yes, sir.
Right. Good question. Right. Now, what I said was for relative velocity, right? For relative velocity, how we express the vectors on the Cartesian plane, right? Or let me say, the most efficient way to approach problems based on relative velocity, right, is how we express the vectors on the Cartesian plane, right? So the way we express the vectors on the Cartesian plane, right, must be such that between the two objects, right, one we identify as the object, the other one we identify as the frame of reference, right? So the one that we regard as our object, that one we draw in a direction that is the same as the one that's been given on the diagram or on the problem statement, right? So because B is the object, right, we draw B on the Cartesian plane in the same direction as the one that's been given. So in the diagram, they said B is going south. So because B for this, we are taking as our object, we draw B going exactly in the same direction as the one we've been given, right? And then I said that for the frame of reference, so for this problem, our frame of reference is A. Now, the way we draw or the way we represent the frame of reference on the Cartesian plane is by drawing it in a direction that is opposite the one that you've been given, right? So the one we've been given is, this is going in that direction. But because we regard this, for this problem, we regard A as our frame of reference, it means we have to draw it in a direction opposite the one we've been given. Are we clear here? That is why this vector is going in this direction.
Yes.
Why? Because it is the frame of reference. Are we clear here? Was that right?
Yes, sir.
Are we good?
Sir,
I add to your explanation, sir.
Sorry?
sir, with
I
what
add
you
to your
said now, sir,
explanation.
Can you add?
Yes, sir.
Sure.
Yes, the way I look at it, and the time I was watching the videos, I noticed that you must draw an arrow to show the direction of where the object is going. So now, if you put the arrow on your line when you're drawing direction of where the object is moving to, it makes it easy for you to determine the opposite direction of where it should be at. In terms of adding to what you were explaining to the guy that I had a question of why the green line must be on this side, not on the other side.
Yeah. Totally agree there. Ryan?
Okay, so yes, I see now.
Do you get it, my guy?
Yes, sir.
All right. Any more questions? I feel like someone was saying something and we cut them off.
sir.
Yes.
I think in the video that you drew it like as is, you didn't draw it in the opposite direction.
That's fine. We are refining what you learned now. That's what we are doing. We are refining what you learned, right? That is, so remember I said the most efficient way of doing it is this one, right? I'll explain why I am not, why I prefer not to take that attempt, right? Because you can do that, but to do that, then you would have to, or I'll explain that just now. I'll explain it just now.
Okay, sir.
Right? But what we are doing now is refining what you already know.
So that's what I was confused about, because I was
confused,
wondering
Ryan.
why it was different, but it could be either way.
Yeah, don't be confused, right?
Yes,
We are
sir.
refining the skill now. We are refining the skill. Right? It is essentially the same thing, but this one, right, is much more efficient, more straight to the point, right? And also you negate having to, I'll explain just now. Right? In fact, let me explain quickly. Right? So the one you saw on the channel, right? Here's a Cartesian plane. So we draw A in that direction. That's VA. And that's VB. That's what you're saying, right?
Yes, sir.
And then we'd have these two components, right? You'd have VA. This is VA cos. Cos, not this. So this would be VA sine 30. And this one would be negative VA cos 30, right? So now when applying the method of components, right, we're essentially looking for the sum of V, what is this, VBA in the X direction. Now, when using this here, right, when you have drawn the vectors exactly as they are, right, it means when applying the conditions of equilibrium, you have to do so with a twist, right? Remember what we said, how we express relative velocity mathematically, right? When we are looking at objects that are parallel to each other, right? I use an example between objects A and B and said you would say, if say, like in this case, B is the object and A is the frame of reference. So this would be VPA is equal to VB minus VA, right? So when I say, when using this, right, you would apply conditions of equilibrium, but now with a slight twist. The slight twist being you have to make use of this here, right? So essentially, you would say, since B is the, what is this? The object. So you would say VBX minus VAX, right? This is what you're referring to, right?
Yes, sir.
Right. Now, what I'm saying is we are refining this now, right? Because I've noticed over the years, this can sometimes throw the students off, right? Because we are applying conditions of equilibrium, but not really, because we have to add this here, right? So to negate having to use this, the way I instead express relative velocity is by drawing the frame of reference in a direction that is opposite the one that's been given, right? So this and this method are going to give you the same thing, right? But this one is more efficient, more proficient. Why? Because you are literally applying conditions of equilibrium. Conditions of equilibrium being sum of vectors in one direction, right? So sum of vectors in the x direction as well as sum of vectors in the y direction. There is no minus. There's no subtracting any vectors. Are we clear?
So to put it simply, the difference is that you're just basically changing the signs.
I wouldn't go as far as saying I'm changing the signs. I'm getting rid of this sign.
Yes, sir, but what I mean is like the positive 160 sine 30 would become negative. And
Yes.
Then, yeah.
So essentially, it becomes the same thing.
Okay, so.
Capish?
So the VBY pink part,
Second?
should that be negative? Should that be negative?
Yes. Right. Are we together now here?
Yes, sir.
Right. So yes, this should be negative since it's headed south. Nice catch there, friend. Right. Are we together here?
Yes, sir.
Sorry, sir.
Yes.
The VAY
Yes.
should be negative because of where it is on the Cartesian plane, because of the Cartesian plane where you get the negatives on the bottom y-axis and
yes, 100%. Because it's headed south. Remember, right? Vectors have directions. So because this is headed south, then we take it as negative. This one we take it as positive because it is headed east.
thank you.
All right. Any more questions?
Sorry, sir. I have a question.
Yes.
On the smaller example that you had earlier,
Mhm.
where you wrote that the velocity of car B, you wrote it as 160 sine 30. Now, since it's since we were trying to add it onto the y-axis, shouldn't it be 160 since 60 degrees, like since 60?
Okay. You lost me there for a second. Just say that again.
Um,
You're referring to
yeah,
this?
sir. Yes, like thereby the small example where it says VA sin 30, shouldn't it be VA sin 60? Since that degree
Okay.
is
No.
closer to the line.
No. 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 Right. So remember what I said, that in order to express a vertical component in terms of sine, you must have used an angle that is referenced from the x-axis.
Okay, got it.
Right.
Just throwing
Now,
me off for a bit.
sorry,
That was just throwing me off, so that was the only thing I had to ask.
but do you get what I'm saying here?
Yep.
Right. Remember, this vector, right, has an angle that is referenced from the y-axis and one that is referenced from the x-axis. Now, if you want the component of this vector in the y direction to be in terms of sine, then you have to make use of what? Of the angle that is referenced from the x-axis. Right? Always reference your angles from the x-axis. That way, you will never get your velocity, your, what is this? Vertical components as well as horizontal components wrong.
Okay,
Right.
so thank you.
All right. Any more questions? Can we carry on?
Let's continue, sir.
All right. Now, so again, people, the way we represent for relative velocity, the way we represent vectors on the Cartesian plane, right? The vector that represents the object goes in the same direction as the one you've been given, right? And then the direction of the frame of reference, you draw in a direction that is opposite the one you've been given, right? Now that you have all your vectors and you've resolved the oblique vector into its components, now you can apply conditions of equilibrium, right? So essentially we are looking for, right, applying conditions of equilibrium, sum of V, right, which is the object, B, and A is our frame of reference. In the what? In the x direction, this is going to be equal to what? VBx plus, right, plus VAX, right? You see how we didn't now use the negative sign here.
So it's not wrong to do it, but it's just better.
Yes.
Okay, so.
Right? Are we together here?
Yes, sir.
Yes,
Yes,
sir.
sir. So
Right. Then all you do now is substitute. So this is equal to, now B doesn't have a x component, right? So it means this will just be 0, right? Plus VA, or the component of VA in the x direction, which is what? Which is this positive 160 cos. So plus 160 cos 30, right? Now what do we get here? What is 160 cos 30? Let's go, people.
It's 138,564.
564. This is kilometers per hour, right? It is positive, right? Remember, this is a vector. So the fact that it's positive is indicating that this vector is going east. Are we clear here?
Yes, sir.
Yes, sir.
Right. So now we again apply conditions of equilibrium, but for now the y direction. Sorry? All right. So sum of V, B is the object, A is the frame of reference, but now in the y direction. This is equal to VBy plus VAY, right? So now you just substitute, right? VBy, right? This is negative, right? So substituting this, we have negative 110 plus VAY, right? So VA in the y direction is negative 160. So this is negative 160 sine 30, right? And what do you get here? What is negative 110, right? Plus negative 160 sine 30. What do we get?
Negative 190.
Negative, we get negative 190, no commas.
Yes, sir.
Right, so negative 190, which is essentially to say this is 190 kilometers per hour, and the negative sign, right, indicates the direction. So since we're looking at a vector in the y direction and it is negative, it means it is going south. Are we in agreement here?
Yes, sir.
Right. So now you have both the x and y component, right, of your resultant, right? Now we are going to calculate the resultant. That resultant is going to represent what? The velocity of B relative to A. Are we clear here?
Yes, sir.
Right.
Sure.
Now in getting the resultant, right? Instead of calling this the resultant, we know the resultant is what? Is actually the velocity of B relative to A. So we call this the velocity of B relative to A is equal to, then now we apply the square root. Right, the square root of the sum of V B A in the x direction squared plus the sum of V B A in the y direction squared. Right, using Pythagoras basically. Right, so now we substitute. Right, in substituting, we said this is equal to 138. So this is 138, 564. So 564 all of the squared plus this is 190, right? All of this squared, right? So remember, at this point, you do not include the negative sign, right? Because you've already accounted for the negative sign by saying this is actually 190 kilometers per hour south, right? So we no longer use a negative sign here because we've already accounted for it by indicating the direction. Are we clear?
Yes, sir.
Right, so what do we get here? What is the square root of 138,564 squared plus 190 squared?
190.364.
364. Wonderful. Kilometers per hour, right? So the velocity of B relative to A is in magnitude 190,364 kilometers per hour. Are we getting the same thing here?
Yes, sir.
Right.
So I don't know if I made a mistake, but I got 235,159.
So you want me to calculate this on my own? Square root of
Mid
138,364
235.
squared. All right, so I'm getting 235.
Yes, sir.
You guys don't know how to use calculators. My God.
235,159.
So I am getting 159. All of you are getting the same thing.
159,
Yes,
yes.
sir.
Yes.
Right.
235,
Yes, sir.
159, yes.
So 159 kilometers per hour. Right. That is the magnitude, right, of the velocity of B relative to A. Right. Now, velocity is a vector, so we also need direction. Right. We also need direction. Right. Now, as far as direction, essentially we've been given because we know that as far as VP with respect to A, right, it is headed in an easterly as well as southern direction, right? So the best way to calculate your direction, right, is by sticking to what you already know. What you know is always reference your angles from the x-axis, right? Just stick to one thing, right? You can, if you want to reference your angles from the y-axis, that is fine, right? But the reason why I say reference your angle from the x-axis, right? Because on your formula sheet, right? On your formula sheet, this is what you have. I said tan theta is equal to sum of fy divided by sum of fx, right? So we're obviously not using forces, but what I'm saying is this is likely what you're going to have on your what is this? On your formula sheets, right? Now, if you use this angle, the angle that you're going to get is going to be referenced from the x-axis, right? So because we are using velocity, so this will be the sum of VBAY divided by the sum of VBAX. Right? So if you use this, you are saying the angle that you're calculating is reference from the x-axis. Right? If it's reference from the y-axis, then it will be tan theta is equal to, so this will be the other way around. So this will be at the top, this at the bottom. So the sum of VBAX divided by the sum of VBAY. Right? So when using this, right, you are saying the angle that you're calculating, you have reference from the y-axis. Are we clear?
Yes,
Yes,
sir.
Right? So continue referencing your angles from the x-axis. Right? And as such, in getting this angle, right, you'll use tan theta is equal to the sum of VBY over what? Over x. Right? So to get this angle, this will be theta is equal to arctan of VBAY, which is 190 divided by the 138,564. Right? And what do you get here?
53,897.
53,897.
Yes, sir.
97 degrees. Right? Now, as we've established that when you use this, your angle that you're determining is essentially reference from the x-axis, right? Between the two directions, which of these two is reference from the x-axis?
East.
East, right? Now, that means when writing down now your relative velocity, being VBA is equal to 235,159 kilometers per hour. That's the magnitude. Direction. Our angle is reference from the x-axis, right? And from our directions, right, the one that is in the x direction is going east. So it means our reference here is east. What is the angle? The angle is 53,897 degrees. Going where? South. Right? So again, if you use this to calculate your angle, you are saying this angle is reference from the x-axis. This angle is reference from the x-axis. If your angle was reference from the y-axis, so essentially, had you calculated this the other way around, that would be 90 minus 53,897. So your angle, had you calculated it the other way around, that's saying your angle is reference from the y-axis, then instead you would have gotten, because that angle would have been reference from the x-axis, you would instead have south first, 36,103 degrees east, right? So when your angle is reference from the x-axis, right, this is how you write your direction, right? Your direction of reference, the angle, and where it's going. Are we clear here?
yes, yes, sir.
Right? So both of these are correct, right? But to make your lives easy, always reference your angles from the x-axis, because when resolving oblique vectors, you reference your angles from the x-axis anyway. So just reference all of your angles from the x-axis. All right. Any questions?
You can continue, sir.
No, sir.
Right. So this is how you would apply the method of components. Right. So this is exactly how you would apply the method of components. Right. Right. Now let us do the very same problem, but now using the parallelogram method. All right, so we're going to do the very same problem. So we are going to do 1.1.1, but now using the parallelogram method. All right, when using the parallelogram method, you already know these are the answers you must get. The answers must be exactly the same. Are we clear here?
So what's the difference between that method and this?
Well, for one, the parallelogram method, you would have to draw a vector diagram. You would actually have to draw a parallelogram. Whereas with this one, you just draw the two vectors, right? You just do you just represented the two vectors, right? You realized one is an oblique vector. You resolve this into its components and applied conditions of equilibrium, right? With parallelogram method, right? We don't make use of what is this? Applying conditions of equilibrium. Instead, we'd use either the cos rule or sine rule.
Okay, so would that need to be drawn with a protractor to be accurate?
Yes.
Okay.
To be accurate, you would need to use a protractor. That's correct. Or let me say, there are cases where you would need to use a protractor, right? And other cases, right, because of, like for instance, now that you're going to do a parallelogram method, right? We know one vector, VP, is going to be in this direction, and this one will be in that direction, right? So for such a case, you wouldn't necessarily have to use a compass, not compass, what is this? Protractor, right? You wouldn't necessarily have to use a protractor because you know this one, right, is parallel to the y-axis. It's only this one that is at an angle, right? So you can essentially take a guess here. It won't really matter because as much as for some cases you would need to use a protractor for accuracy, right? We do not necessarily then use the graphical method in determining the vectors, right? The use of a protractor is to know exactly where your resultant is going to be, right? But for such a case, you know the resultant is going to be on this quadrant. Why? Because both essentially, what is this? Both vectors are on the same quadrant, right? So only on cases where the vectors, right, are essentially on two different quadrants, right, you never really know where your resultant is going to lie. That is why in that case, you would then have to use your protractor. Are we clear here?
Yes, sir. And one more thing, sir.
Yes.
In like an exam, would we have a choice, or are there some cases where you have to use one or the other?
So there
method?
are cases where you have to use, like for instance, look here. I will be sending you this document after the class, ne? So I want to show you what I mean by sometimes the examiner. Right. You see this one?
Yes, sir.
Above sketch represents a plane of such and such course by wind. So you see, if you're not familiar with parallelogram method or vector diagram, right, this could easily, what is this, throw you off. Right, so I mean for such questions where you are either given the vector diagram or you are asked to draw the vector diagram. Are we clear here? So because we don't know how the examiner is going to ask the question, the examiner can say using a vector diagram, right? That is why you need to be comfortable with both methods. Also, in N6, right, it is going to come in handy, right? Being comfortable with the parallelogram or vector diagram, right? There is a module in N6, Mechanotechnics N6, called Kinematics. You are going to make use of a vector diagram, right? So that is why we teach you both methods in N4, so that when you get to N6, you are comfortable with both methods, because you are definitely going to need them. Are we clear here?
Okay, sir. Thank you.
Yes, sir.
Right. So now we are going to look at the same problem, but now using the parallelogram. Right. So this is still 1.1.1, but now we're using the parallelogram or vector diagram. Parallelogram method. Right. Right. So essentially, we are going to do the very same thing. Okay, let's do this. Have the Cartesian plane. So you draw your Cartesian plane. You draw your Cartesian plane, right? And then you represent your vectors, right? You already know P is the object, A is the frame of reference for 1.1.1. So you are going to have, now again, because for this problem in particular, the vectors are such that, what's going on here? The vectors are such that they are on the same quadrant. Right? So this is B going in that direction. And then VA, remember, we are going to draw in a direction opposite the one we've been given. Right? The one thing we took note of is that the vector of A is at an angle of 30 degrees with the x-axis. Right? So B was 110 and A is 160. So make this one slightly longer. Right? And we know this is in that direction. And we know that this here is 30 degrees. Right? Now, in completing your parallelogram, right? In completing your parallelogram, all you do is, right? All you do is here, you are going to have this vector drawn from this end. So essentially, you draw a Cartesian plane there, right? But for this case, you do not necessarily have to draw a Cartesian plane. Why? Because you know that this here is parallel with the y-axis, right? Or maybe if you do want to be extra accurate, then you can draw a Cartesian plane here, right, on this end of this vector, right? And draw this vector at this end, right? Once you have that, once you've drawn this vector, or once you've drawn this vector on this end, all you do is you connect these two lines, right? Because once you've drawn this vector, right, essentially by connecting these two lines, this line that you draw here will be exactly equal to this one here. Right? If you duplicate this one, it's exactly the same, right? And then you know these two were to complete the parallelogram, right? Now, in completing your parallelogram, right, where the two vectors meet, which is at this point, that is the direction your resultant is going to take. So your resultant, you know, at this point is going to go in this direction, right? So it's going in that direction where the two vectors essentially meet. Right, and this would be your complete parallelogram. Any questions here? Hello?
No questions here, sir.
Still good.
Right. So once you've completed your parallelogram, right, we know this vector here is 110, right? This is 110. It is 110 kilometers per hour, right? And then this one is 160 kilometers per hour. All right, so that's one. Right. Now what you do next is you are going to label your parallelogram. Right. So for instance, if say this is A, call it B, call this C, call this D. Okay, I used small letters, supposed to be capital letters. So that's A, that's B, and then that's C, that's D. Right. Once you've labeled your parallelogram, right, remember what it is that you're looking for. We're looking for the resultant, which is this one. The resultant represents what? Represents the velocity which you're looking for, which is the velocity of B relative to A. Right? So now you work out your angles, right? Now, if this here is 30 degrees, we know this entire angle is 90 degrees. So if that's 30, what is this angle equal to?
60.
So we know that
Please.
is right. Now in a parallelogram, opposite angles are the same, right? So if this is 60 degrees, it means that's 60 degrees, right? And then we know this angle is co-interior with this angle. So if this is 60 degrees, what is this angle equal to? So the question is, if this here is 60 degrees, right? And this angle is co-interior with this angle, right? So if that's 60 degrees, what is this angle? Do you guys remember co-interior angles? Co-interior angles sum up to what? 180.
$120, sir.
Do you see this U here, right? This is a U. Do we see that?
Yes, sir.
Hello?
Yes, sir. So it's 150.
It's 120.
It's 120 degrees, right?
It's 120, yes.
Yes. So if this is 60, we know the sum of this angle and this angle is 180. Why? Those are co-interior angles. So if this is 60, it means this angle is 120. Yes.
Oh, yes, I looked wrong. I looked at the 30 instead of 60.
Oh, okay. So this angle is 120. Yes. 120 degrees. All right. So that angle is 120 degrees. Right. Right. So now we are going to choose a triangle we are going to work with. Right. So for instance, we are going to choose triangle ABD. Right. We are going to choose angle ABD. Right. The triangle you choose doesn't really matter, because if this is 120 degrees, this is a parallelogram and opposite angles are equal, meaning this being the opposite angle of this one means that this is also 120. So you could also use BCD. Are we PA?
Yes, sir.
Right. But for the purposes of this exercise, we are going to choose ABD. Right. Now, if you look at this angle, right, if you look at the angle 120 degrees, right, would you say this angle is an included angle? Now, an included angle is an angle that is between two sides, right, that are meeting at the same point, that we know the value of, or that we know the magnitude of.
Yes, sir. It's an included angle.
It's an included angle, right?
Yes.
So if the angle you have on your parallelogram is an included angle, then we make use of the cosine rule, right? If the angle you have is such that it is an included angle, then we make use of the cosine rule. But if the angle that you have is not an included angle, then you make of the sine rule. Do we understand the difference here?
Yes, sir.
Right? So if the angle you have is an included angle, then you make use of the cosine rule, right? So now we say in triangle, right? In triangle A, B, D, right? Now remember, as far as the cosine rule, right? Cosine and sine rule, right? We have to label our triangle, right? The side opposite the angles, right? We name as small letter. So for instance, we have this side as being A, right? This represents A. The side that is opposite this will be small letter A. So this will be small letter A, right? And then if we have B here, the side opposite B is this one. So this will be small letter B. So this will be small letter B, right? And then you have D here. The side opposite D is this one. So this will be small letter D. So this is small letter D, right? And then in using the cosine rule, seeing that the angle we have is an included angle, right? What are we looking for? We are looking for A. So we then say A squared is equal to B squared plus D squared minus 2BD times cos what? The angle we have is cos A. Are we clear here? Right, this is the cosine rule.
Yes, sir.
Yes, sir.
Right. Now we're looking for A. We're looking for A, right? Seeing that A is the what? Is the resultant, right? Or the what? The velocity of B relative to A. Right? Just like with the method of components, the resultant there was the velocity of B relative to A, right? So with the parallelogram method, the resultant thereof is also what? The velocity we're looking for. So in this case, we're looking for velocity of B relative to A. So this green line being the resultant represents the velocity of B relative to A, right? Now we substitute, right? A squared is equal to B squared. B squared, what is B equal to?
160.
110.
So B is equal to 160. Remember, in a parallelogram, opposite angles, the same, opposite sides, the same. So this side is opposite this one, right? Meaning that this is equal to 160. That's B here. Are we clear here?
Yes, sir.
Yes.
So this is 160 squared plus D squared. And what is D equal to?
110.
So D is equal to 110. So that's 110 squared minus 2 into B squared. B is 160, right? D is 110 times cos A. A is 120, right? So what is A squared equal to? So what do you get here? What is 160 squared plus 110 squared minus 2 into 160 into 110 times cos 120? What are we getting here?
Cos 120. Okay. So that's the angle we're working with.
Two 235.159.
Okay, so I'm looking for A squared. What is A squared equal to? So as in, what is this whole thing equal to?
Is 235.159.
So that is what A is equal to. I am looking for, what is this here? What is this equal to? So what is 160 squared plus this minus that?
55,300.
So this is 55,300. Then to solve for A, you apply the square root on both sides. Therefore, A will be what? The square root of this. And this is equal to 235, 1595. So let's say 16 kilometers per hour, right? Essentially meaning VBA is equal to 235,16 kilometers per hour. Are we getting the same thing?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
Right. So you have the magnitude of the resultant being VB with respect to A, right? But as we know, VPA or velocity is a vector, so we need direction as well, right? And our direction is going to be such that it is referenced from the x-axis, right? So essentially the angle that we need to get, this being our vector, right? We want our angle to be referenced from the x-axis. It means the angle we are looking for is this one here. So we are looking for this angle because that's the one that is referenced from the x-axis, right?
Yes, sir.
So now to get that angle, right? To get that angle, right? We again make use of triangle, what is this, ABD? So meaning we are going to calculate this angle here, right? We are going to calculate this angle, right? And then in calculating this angle, right, to get this entire angle, we're simply going to say 90 minus this angle, which will give us this here, which is what we are looking for. Right? So now we are looking for angle B, essentially, since we're looking for, or since we're using A, B, D, it means we're looking for angle B. Right? Where's this thing? Right? So using the sine rule now, we are looking for sine B, looking for angle B. Right? You divide that by, where's this thing? We divide that by the side opposite the angle, which is what? Side B. So sine B over B is equal to, right? This is the angle we have, right? This is the angle we're looking for. The angle we have is this one. The side opposite is the resultant. So we're going to say sine A. So sine A over what? Over A, right? So now you simply substitute. So this is sine B. We're looking for angle B. Side B from our parallelogram is equal to 160. So that's 160 is equal to sine A, which is the angle we had, which is 120, right? Divided by side A. Side A is our resultant. Our resultant is 235,16, right? So now in solving for B, right, you multiply both sides by 160. So you will end up with sine B is equal to sine 120 divided by 235,16. This multiplied by 160, right? So this essentially is 160 sine 120 divided by 235,16. And then to get the angle, you simply say the angle we're looking for, B, is equal to arc sine of 160 sine 120 sine 120 divided by 235,16. And what do we get here? what is the arcsine of 160 sine 120 divided by 235,16? What are we getting?
36,103.
So 36,103 degrees, right? That is B. So that is this angle, right? That angle is referenced from the y-axis, right? And then if you remember when we did the method of components, remember the angle we got? That was referenced from the y-axis. Do we see that it is exactly the same?
Yes, sir.
Do we see that?
Yes, sir, we see it.
Yes, yeah.
Yes,
All right.
sir.
Right. But we are looking for what? We are looking to reference our angle from the x-axis, right? So in getting the angle that is from the x-axis, we know that this angle, the whole angle is 90 degrees. So to get this one, we'll simply say 90 minus the one we just got, and we'll get the angle reference from the x-axis, right? So we say theta is equal to essentially 90 degrees minus 36,103. All right, so 90 minus 36,103, we get 53,897 degrees. Therefore, meaning VBA is equal to, in magnitude, 235,16 kilometers per hour. Direction, the angle is referenced from the what? The x-axis. As far as the x-axis, right? As far as the x-axis, is this resultant going west or east?
East, sir.
Right? It's going east. So our angle having been referenced from the x-axis means this is east. The angle is 53,897 degrees. Going where? South.
South.
Yes. Right? Now, you do not necessarily have to do this, right? Because the angle that you calculated was inadvertently referenced from the y-axis. You can just keep that, right? So meaning you could have said your VPA right? Say, or your VPA. Now this angle, right, as we've established, is referenced from the y-axis. As far as the y-axis, the direction is south. So this would have been south. Angle is 36,103 degrees, headed where? East, right? So instead of doing this, so I mean for now exam and what is test purposes, right? You would obviously realize that this is actually the angle that is referenced from the y-axis, right? And then you would use this instead. Are we clear here?
Yes, sir.
So, because we always work from the or towards the x-axis, it will always be east or west first before the degrees.
So if you
Alright.
you say you are sticking to referencing your angles from the x-axis
From the
always,
x-axis, yeah.
yeah. So it will always be so this here, right? So the first direction, right, is where this angle is referenced, right? So this, it means for you, will always either be west or east, right?
Okay.
The first direction always represents where your angle is referenced from.
Thanks for that, sir.
Sure. Any more questions?
Yes, Manyar. I just want to know, man, how do you include get the how to see that this angle, that 120 is an included angle? How to see that one? How to
Right.
determine when this equation?
So an included angle, right, for the cosine rule, an included angle is an angle that is between two known vectors, right? Remember, we determined this 120 degrees, right? Right, from the basis that if this is 60, we know this angle is coincident with this one, right? So we essentially subtracted the 180, right? We essentially subtracted the 60 degrees from the 180 to get this angle, which is 120, right? And then if you look at this
Thank you
angle,
very much.
it is between two known vectors. We know this vector and we know this one. So meaning this is an included angle, included between two known vectors. Are we clear here?
Oh, okay. So to get 120, you minus 120 to 180 to 6 to 180.
Yes.
That means that is an included angle because 180 on this fourth quadrant is minus most. The theta is minus.
Right.
Okay, I got it one. I got one. Unless you now I had it seems like you are referring to 110 and then to 160 because of the vertical and 160 as a resultant
Not as a resultant.
So
remember the resultant
okay.
is this one.
As a side,
Yes.
as a resultant that one now.
So you
as
mean
a
this
side.
one?
Yes, I mean this one. So now your explanation, you are looking as the angle, or you are referring to the sides 110 and 160. Then that's when you can be able to get 120.
So as far as the angle 120, right?
Yeah.
As far as the angle 120, remember we established that if this here is 30 degrees, right?
That's correct.
We know that
yes.
This entire angle is 90 degrees. That means to get this angle, right, we are going to say 90 minus 30, and this becomes 60, right?
60.
And then what I said was,
and then
because you're looking at a parallelogram, right? In a parallelogram, opposite angles are equal, right? And then I made note of the fact that if you look at this here, right? Essentially,
yes.
let me make this. If you look at this, make this orange, right? If you look at this here,
yes,
right? You essentially have a U there. Do you see that U?
Yeah.
So
Yeah, that's you. Yeah,
since you have U here, it means this angle is co-interior with this one.
With this one.
So because those angles are co-interior, right, it means the sum of them is equal to 180. Now we had already established that this is 60. So since this is 60, it means this is 180 minus 60, which is 120.
20.
Right? Then
now it's an included.
Now it becomes, this angle becomes an included angle because it is between this vector and this vector, and both vectors are known. We know this is 110, and we know that this is 160.
Okay.
That is why this is an included angle. It is included. It is an included angle because it is between two known vectors.
Okay. Thank you, Manuel.
Sharp. Next. Any more questions?
So, with the labeling of the triangle that we worked out, how do we determine which value goes where in the formula, the cosine formula? Because if you switch it around, you get a completely different answer.
You won't get a different answer. Right.
Either.
So remember here, you won't get a different answer. Right. Say we use the triangle ABD, right?
Mm-hmm.
Now from that angle, once we had established that this is an included angle, hence we are going to use the cosine rule, right? You then look at what exactly we are looking for. We are looking for this side.
Okay.
Right? We are looking for this side.
Yes.
Now, the way you label your sides is by using the letters that you've already been given, right? How you do that is you've already been given A, right? The side that is opposite this, that is opposite A, you are going to label as small letter A.
Okay.
So this becomes A virtue of that, right? You have D, side opposite D is this one, so this becomes small letter D. So this becomes D, right? You have B, right? The side opposite B is going to become small letter B, right? So that becomes B, right? Now, as far as how you write out your cosine rule, right? You base it on which side you are looking for. You are looking for side A. So you make A your subject.
Okay.
Right. So making A your subject, it means your cosine rule will be A squared is equal to B squared plus D squared minus 2PD cos the angle of what? Of A. So this being your subject, right? It means the angle here is going to correspond to how you label this. So if this is A, then this is going to be angle A. Had this been B, then this would have been angle B. Capish?
Okay, thank you.
Any more questions?
No, sir.
All good.
All righty then. So I'll be sending this document in the group, right? You guys are now going to attempt 1.1.2 using both the method of components as well as the parallelogram method. Right? The answers you get, you know by now, must be the same. Right? I'm also going to send you past exam questions, which you are going to use as your study packs. Right? You're going to attempt any and all questions that you come across based on relative velocity. Right? Tomorrow.
Can I ask a question?
Sure.
Okay, just if we go back just a little bit, why did we decide to minus that angle B from 90 instead of 60?
Which angle? You mean this?
The last, let's go down on the parallelogram, the theta.
Right. Why did we say 90 minus this instead of 90 minus 30?
Perhaps 60. We said we know that angle between can we go up to the parallelogram?
Yes.
Yes. We said if we have the whole angle is 90, so we know the angle on the parallelogram it's 60. So why do we minus again from 90 instead of 60?
Right. So had we said 60, so this angle we know is 60. That's what you're saying, right?
Yes, we know the angle is 60.
Right. So had we said 60 minus this angle, we are going to get this angle. So meaning we would then have to add the 30 degrees. It was going to take longer for us to get the angle that is referenced from the x-axis.
All right.
Do we see that?
Yeah, it's noted.
Yes, sir. Any more questions? Right. So tomorrow I will do a video on resulting velocity. Right. I will be posting that in my channel and sending to you guys in our WhatsApp group. Right. So that you are going to watch. And then I will then send subsequent programs that you can do as homework. Are we clear here?
Yes, sir.
Right.
Yes, Menier.
And then in our next section, for next week, we're going to have 2 sessions. We're going to have 2 sessions, possibly 3. We might need to have a session on the weekend or during the weekend. Right. But I will be doing videos on relative velocity. Right. Tomorrow, I'll do a video on not relative velocity, resulting velocity. Right. And I will post in the channel. So you will go through that. Right. And then next week, I'll also be posting more videos. Right. And then, of course, I'll be addressing questions during our live session.
So I just have one more question.
Yes.
Is it possible for you to tell us what formulas we need to know that aren't on the formula sheet?
No, all of them.
Oh, okay.
It's very simple for science. Know all the formulas, right? The formula sheet is not reliable.
Okay, sir.
I will clear. Maybe let me show you something. Okay, yeah. Let's look at the formula sheet. See, it's only one page. These are all the formulas on the formula sheet. Not reliable at all. You must know all of them. I will clear you.
Yes, sir.
Yes,
Do you
sir.
see what I
Yes,
mean
sir.
here? The formula sheet is literally one page, and there isn't many formulas here, as you can see. So know all your formulas off by heart.
So it's tough for me who has a 1 gig memory.
My guy.
Good one.
My guy.
So sorry,
Yes.
sir. I just want to ask a question. There was a communication that was sent with regards to the test that if you are 80 kilometers outside the borders of the campus, you can send a request to you to say that can I write maybe online?
Yeah. That
Right.
part we are going to discuss tomorrow. I will be sending you something, and you guys can choose, for instance, the time slot that you want to write the test at, right? And then as far as the guys that fit in the category of being able to write the test online, right? Yeah, we'll talk about that tomorrow, because there's one thing I still need to figure out, or with the PM, with my program manager,
All right.
as to who exactly is going to be what is this, be the invigilator for that test. But for now, don't worry about that.
Okay.
Right? Worry about
Now that
Kinematics.
you're raising, sorry, now that you're raising we're going to communicate tomorrow. Do we still have a session or we don't have the session?
No, tomorrow we don't have a session. Remember, I said because we started
Okay.
at 6, tomorrow we won't have a session.
Okay. No, thanks.
All right.
Sorry, sir.
Yes.
Yes, I just want to understand our sessions allocated an hour each session, each day.
Not necessarily. That's how it's supposed to be, but that's not how I'm going to do it. Right? Our sessions will run as long as they need to.
Okay, that's good.
Sure. Any more questions?
So I have a question.
Yes.
Will we also be covering heat on this block?
My guy, we are not skipping anything.
Damn it, I thought I got lucky. Okay, that's all my questions.
Sure. Next.
What is there?
Yes.
Is there anything that you could share with us on the group or something that is you use on your device? Yeah.
No, my guy. This my digital textbook can't be sent, right? I have to use, or we use it using that platform, right? It's not a book that I can send to you guys. It's not necessarily a PDF book, right? I can only access it through that platform. So no, there won't be any book that I'll be sending.
Okay.
But in fact, I've borrowed some of you what is this, engineering science books. Because I know that what is this, that Ubuntu whatever, it's not that reliable. That's why I borrow students hard copies. Any more questions? So if you need a textbook, my guy, you can come to Wingfield campus. I can borrow you a textbook.
Okay, sorry, sir.
Yes.
One more last question. Is there any specific recommended book? Because I did got a book today from Wingfield campus, which is the white covered the white front page book.
You didn't get the book at Wingfield campus. You got it from Mr. Mtetwa.
Yes, I did got it from Mr. Mtetwa, the white one on the outside. Is it the? I wanted to understand, are all recommended, or is there a specific one that is recommended for the course?
Who do you think you are talking to? This is Mr. Mtetwa.
Come on, sir.
Chief, this is Mr. Mtetwa. I gave you the textbook, so obviously I gave you the best textbook. It's like you think Mr. Kotongan and Mr. Mtetwa are two different people. It's the same person.
Oh, okay. Because
this is the nature God. That's me.
Yeah, I was trying to get hold of you on the phone, but then there's
a very
two.
busy person. Remember, I'm sure when you arrived there, I was lecturing. I'm sure.
Oh, okay. I get you now.
So if I gave you the textbook, that's the recommended textbook.
Okay, that's quite.
All right. Any more questions?
So for the first test, it's relative velocity, projectiles, and just beams from statics.
Yes.
Yes, sir.
And resultant velocity, no?
Resultant velocity, yes. I think he said so as well. Right?
Yes, sir.
At the native God.
One and only.
Why did you? Yes. Why did you guys change it now? I know we used to submit the test via email or Google Classroom.
So it's a long story, my guy. It's a long story. We remember we had a session, I think last week, with you guys. That part was covered. It's a long story. Right.
Okay.
If you need to know that, you can come and visit me at Wingfield. But it's a long story.
Sure.
I don't want to cover the story here on this platform.
Okay.
Next. We good?
Yes, sir.
All good, sir.
No questions.
Yeah, meneer, also right.
All right, wonderful. So just make sure you do the work, guys. With science, there is no getting over the hump without actually doing the grind. You have to do the work. Right? I'll be sending you a study pack. Right? Make sure to go through the problems on that study pack. Right? And then, of course, if you need me to answer some questions based on your solutions, that we can discuss in the group.
That's perfect, sir.
All right, then. I will be posting a video tomorrow, so watch out for that video. Right. As far as relative velocity, essentially we are done because we've covered both methods. Right. There's absolutely nothing else to it. Right. Method of components, that is how you do it. Parallelogram method, I showed you how to do it. There's absolutely nothing else to it. Right. The most important thing here is understanding that for both methods, right, the object you take as the object, right, you draw in the Cartesian plane in a direction that is been given, right, and then the frame of reference you draw in a direction that is opposite the one you've been given. That's the most important thing here. Light?
So are you gonna post videos where there's the one with the questions with distance?
Yes, I'll cover those as well.
Okay, thank you, sir.
All right, sharp. Right, I think we're done here. Right, so good luck with your studying, guys.
Thank you so much, sir.
Thank you very much. Have a good evening.